Good afternoon, ladies and gentlemen. Welcome to the last day of the 9th ITB International Geothermal Workshop 2020. My name is Angga Bakti Pratama, lecturer of Geothermal Master Program ITB, and I will be your host for today's occasions. Special this year, our event previously postponed has been modified from physical to online basis event. This year's event is also coincide with celebration of 100 years of ITB. Happy 100th years birthday to ITB. You made a tremendous journey. Our annual event is organized by Geothermal Master Program, Institut Teknologi Bandung, with a theme of this event is advancing the prospecting and utilization of national geothermal sector through best practice management, investment, and technology. This event is sponsored by PT Sustrako Adi Kreasi as a silver sponsor, PT Geothermal Energy as silver sponsor, PT Tunggal Buana Utama, PT Pelumpang Raya Anugrah, PT Scientific Drilling, and Star Energy Geothermal as a bronze sponsor. And our other sponsors are PT Pertamina Geothermal Energy, PT Supreme Energy, PT Sarana Multi Infrastruktur, PT Depri Wangga, Kogindo Daya Bersama, Bank Nasional Indonesia, and PT Andalan Tunas Mandiri. This event is also supported by International Geothermal Association, Indonesia Geothermal Association, Indonesia Association of Geologists, and our gratitude also goes to media for advertising this important event. Think Geoenergy, Geothermal Research, Madrock Media, Panas Bumi News, Indonesia International Geothermal Convention and Exhibition, Rambu Energy, and Wing Indonesia. More important, this event is free, and don't forget to subscribe in our YouTube channel. The link will be provided in the chat box of this Zoom. Make sure to check your chat box at the end of the event to get a free e-certificate as well. Today's technical session, we're going to have one invited speaker, Mr. Alfredo Battistelli, Geothermal Reservoir and Engineer Consultant, and other 5 selected speakers that will present their findings. Today, we will have Mr. Heru Berian Pratama as moderator to lead us through the technical sessions. Bapak Heru, curriculum vitae is as shown on your screens. Bapak Heru Berian Pratama is a lecturer in Geothermal ITB Master Program. He has a lot of experience such as academic assistant, research member, and also trainer and organizer of for the training. So, Bapak Heru, most welcome. The time is yours.
Good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Heru Berian Pratama, and I will be the moderator in the last day of IIGW technical session. First of all, I would like to welcome you all participants in Zoom and YouTube to the technical session. The topic of today's session is engineering. Furthermore, we will present wide range of geothermal engineering subjects such as numerical model, power plant, production, and artificial intelligence. In this occasion, we shall have outstanding presentation from our prominent presenters, whom I believe shall enrich our insight and knowledge regarding the theme of this workshop. Today, we have one invited speaker and 5 presenters from different institutions. The invited speaker is Alfredo Battistelli, and the first speaker we have Afiat from ITB. The second speaker is Jooned Hendrarsakti from ITB, Zagy Yakana Berian from ITB, Andrian Putra Wardana from ITB, and the last but not least is Galih Kusumo Wardoyo from PTPLN. Please welcome to you all in the IIGW 2020. And now we will hold a photo session. The committee will invite you in this Zoom. First, Alfredo Battistelli, and then Afiat, Jooned Hendrarsakti, Zagy Yakana Berian, Andrian Putra Wardana, Galih Kusumo Wardoyo. Okay, for all distinguished presenter and speaker, please hold your smile on the screen and the committee will take our picture. I will count to 3, 1, 2, 3, smile. Okay, thank you very much. And as a token of our appreciation for your valuable contribution, there will be a memento for you, and the committee will contact you regarding the CP address. In the question and answer session, to ask a question, audience may use a quick Q&A feature in Zoom or write your question in YouTube comment section during the presentation. The questions should be in the following format. The first, you should write your name, institution or affiliation, and then the question. Due to time limitation, we will select several questions and continue to remaining if the time is adequate. Regarding the information about e-certificate and attendance list, the committee will notify the participants throughout Zoom chat or YouTube's comment, and the presentation material will not be given. However, full recorded version of our event will be uploaded on the Geothermal ITB YouTube channel. The full paper will be published in the proceeding of IIGW and IUP Conference Series Earth and Environmental Science. Right now, we will start a presentation from the invited speaker, then proceed with technical presentation. Please note that the presentation schedule will follow the event rundowns. Today, the prominent invited speaker is Alfredo Battistelli. His educational background are civil engineering, then proceed master degree in mining engineering at University of Bologna. He has abundance of experience as senior reservoir engineer, and currently he is geothermal reservoir engineering consultant. Ladies and gentlemen, without further ado, please welcome Alfredo Battistelli. The time is yours.
Good afternoon to everybody. I'm Alfredo Battistelli, and I've been invited by the International Geothermal Workshop Committee to give this speech about current and future challenges in reservoir modeling. Actually, I would like to talk more about the capabilities we already have rather than challenges, but let's go to the outline. We will talk about reservoir modeling workflow, the conceptual and reservoir models, the reservoir simulator, inverse simulation capabilities, thermodynamics of geothermal mixtures, the use of tracers in numerical simulation, supercritical condition, modeling of non-condensable gas injection, coupled boilable reservoir flow, and geochemistry and rock mechanics. So this is the typical reservoir modeling workflow for a new field without production history. So we start from field data to build a conceptual model, and we would like to use a 3D geological modeling software. From the conceptual model, we build the natural state model, on which we can already consider the planned production and injection wells for the field development. Then we use the static pressure and temperature logs and the data collected with production, interference, and tracer tests to calibrate the natural state model. And we need inverse simulation co-capabilities for that. Once the model is calibrated, we build the exploitation model considering the requirements for the fluid collection and injection system and the plant requirements. How much steam can we produce? Then, once the exploitation model is ready, then we can simulate forecast scenarios. So we need a reservoir simulator, inverse simulation capabilities, which can be integrated into the reservoir simulator, and wellbore simulator and simulation capabilities for the exploitation model. They can also be integrated into the reservoir simulator. When we go to the modeling of an exploited field, what we have is the field production history, so that we can build a production model and perform the calibration in order to match the past production history. Once this calibration is achieved, and it may need also to recalibrate the natural state model for that, Then we can build the exploitation model and again simulate the forecast scenario. What is the conceptual model? I mean, what we have to use for the conceptual model? We want to use a 3D geological modeling framework. And this modeling framework should also be integrated with the reservoir simulator, because we want to build the discretization grid and the input files for the reservoir numerical model within the same modeling framework. And the conceptual model code shall also be able to visualize the simulation results. Examples of this, which are not exhaustive, of course, are Leapfrog Geothermal, which is a 3D geological modeling integrated with TAF2, which is actually given all of this stuff. And there is Petrel EMP software platform, which is integrated with Eclipse Geothermal, which is also able to do that. Other pre and post processor with less developed geological modeling capabilities are Petrosim, and this is an example of a model developed within Petrosim at the conceptual level, and then the model, the grid built for TAF2. Another pre and post processor is TAF2 Viewer. What we have to model? We do not have to model just the reservoir, but the reservoir with a well field, the production wells producing at separation stations, and the reinjection wells in which the separated brine is reinjected. And the steam is sent to a turbine with a turbine inlet pressure. And then the steam is condensed, and the fraction of steam, usually between 25 and 30%, is recovered and is reinjected back into the reservoir. So what we would actually like to do is to simulate everything. So the numerical simulator requires capabilities. Of course, it has to solve the non-isothermal mass and heat transport of multi-component, multi-phase fluid mixtures in porous and fractured media. We would like to have discretization grid able to follow geological features and allowing grid refinement around the wells. We would like to have stable convergence and fast solution of balance equations, integrated wellbore flow simulation with wellhead pressure control, and a basic integration with the fluid collection and reinjection system and the plants, and the activation of makeup wells for global steam rate support. So, which are the new geothermal reservoir simulator? They are built with updated programming languages in Fortran 90, 95, 2003, and C++ with object-oriented programming. They allow parallel simulation and multi-core machine, cluster, and supercomputers. They have faster linear and parallel solvers and improved phase transition and steady-state convergence behavior. Examples are TAF3, developed by LBNL, ITAF2, and then the new version of the code, also developed at Lawrence Berkeley National Lab, Wildera, which is developed at the University of Auckland, and Eclipse Geothermal, developed by Schlumberger. Now the inverse simulation. This is the basic workflow by ITAF2. So you see that we first set initial model parameters with the model calculate the system response. Then we compare calculated results with measured system response at the field in an object function. And then through a minimization algorithm, we update the parameters in order to improve the reproduction of the measured data. So that we go through a trial and error procedure. We go to the calibration of the input parameters of the model. Now, thermodynamics of geothermal mixtures. I mean, geothermal mixtures are mainly composed by water, of course. So that water, the thermodynamics of water and water properties shall be computed in an accurate way. Usually now we are using the International Association Properties for Water and Steam, the 97 correlation updated in 2007. This is a pressure and temperature diagram in which the only physical boundary is the saturation curve of water here, while the regions labeled as 1, 2, 3, and 4, 5 are regions for different correlations, different equations. Once we add, and you see that in the subcritical simulation, usually we go up to 350 degrees C, which is the boundary of the liquid region with a supercritical one. There are already Other codes able to simulate supercritical conditions. If we add CO2 here or sodium chloride, we have strong changes of the phase behavior of the mixture. So usually in the more general case, when we model subcritical mixtures, we would need a mixture of water, sodium chloride, and CO2. But we chart the most used equation of state module for TAF2 and TAF3. US1 for pure water, US2 for water and CO2, and EWAS-G, which is the three-component model for water, sodium chloride, and one non-condensable gas, usually CO2. Other codes with capabilities for three-component mixtures are Petra, STAR, and TAF plus RGB. TAF plus RGB is for real gas brine developed at the Lawrence Berkeley National Lab. Improvements. We would like to have the thermodynamic equilibria suitable for high partial pressure of CO2 with improved mutual solubility models and calculation of CO2-rich phase properties. There are already codes doing that, or at least partially doing that, as CCO2N developed at Lawrence Berkeley. It was G, the version included into TAF3. There is TM gas, which has been developed for modeling of gas mixtures into geological structure. Again, TAF plus RGB. And we would like also to be able to model mixtures of gases. And codes already able to do that are Eclipse Geothermal, TMVOC, which has been developed not for geothermal application, but can be used also for that. And again, TM gas and TAF plus RGB. Tracers. The main purpose of tracer is to study the connection between injection and production boreholes in order to predict the possible cooling of production boreholes due to long-term reinjection of spent brines. There are tracers for suitable for the liquid phase, for the steam phase, and for the two-phase conditions we can find in reservoir. And the consolidated interpretation with analytical and semi-analytical approaches as described by Axelson. But we can move to numerical modeling. The rigorous thermodynamic approach for partitioning of gas and liquid tracers between the liquid and the steam phases has been developed for TAF2 by Crew et al. In 2001. Now there's a new equation of state module, US1NT, available for ITAF, which allows the partitioning of the tracer using a Nares law for multiple tracer with absorption and decay. And also TM gas can simulate multiple gases and dissolved solids with generalized absorption isotherms and decay of all components. And this can be used as tracers. Let's go to supercritical conditions. Well, we can find supercritical condition when drill deep wells in already exploited high temperature hydrothermal systems. But when we simulate this kind of reservoir with approaches, with subcritical approaches, we can get something like that. This is a model for a field in Kenya, in which wells at 2,000 meters and over the upflow were already measuring more than 400 degrees C. So we were obliged to cut the model in the basement in order to avoid supercritical temperature. Actually, supercritical condition can be modeled already by ITAF2 US1 SC, which provides modeling capabilities for pure water covering the entire PT space of the IF97 correlations. Another possible code is TAF2 US2H, which is for mixtures of water and CO2 that can be used at subcritical condition and steam-like supercritical condition. Steam-like means that we cannot model the region 3 of the PT space because those correlations are not used. Now about the non-condensable gas injection. Usually non-condensable gas are discharged to the atmosphere, but this practice is becoming an issue, even though the life cycle greenhouse gas emissions of geothermal plants are among the lowest. Why? Because non-condensable gas emissions is becoming a concern for the public acceptance of old and new power plants in some country, and I would mention Italy. Moreover, greenhouse gas emissions of geothermal power production might hinder future funding of geothermal projects by international finance institutions. So there are pilot projects and research projects in several countries in order to study the feasibility of non-condensable gas injection, reinjection, and the geothermal reservoir. But in order to do that, we need modeling capabilities for that. So considering the non-condensable gas injection schemes are the injection of a pure CO2 or non-condensable gas mixtures, the injection of NCG dissolved in condensate or in the brine, or the co-injection of two streams of non-condensable gas and brine in the same well. So from the simulation point of view, reservoir simulators are needed with equation of state module able to simulate high-pressure CO2-rich mixtures in equilibrium with sodium chloride brine, and coupled wellbore reservoir flow capabilities, which include CO2 liquid gas phase transition in injection wells. An example is T2 well ECO2M. T2 well includes wellbore flow modeling capabilities into TAF2, while ECO2M is an equation of state module for ternary mixtures with a good thermodynamic approach up to 300 degrees C and 600 bar. It can model three-phase flow, phases of CO2-rich gas, or liquid CO2 and brine, both in the wellbore and the reservoir, and transient wellbore flow in cylindrical and annular conduits using the trade flux model. This is just an example of pressure, flowing pressure profiles in the injection well and flowing temperature profile and the injection well. So now about the coupled wellbore reservoir flow. Modeling of wellbore flow is actually needed for a variety of purposes in both reservoir engineering and modeling studies. Customarily, steady-state wellbore simulators are used for basic applications that fall for when we need a transient solution of coupled wellbore reservoir flow, then we need additional capabilities. And these additional capabilities can be very useful for the interpretation of well tests, both completion and production tests, and for the production forecast simulation with wellhead pressure control. And again, T2 well can provide full transient coupled wellbore reservoir flow capabilities for the TAF2 family of reservoir code. An example is EWAS-G coupled to T2 well, which has been used to model at the same time the well output curve, the flowing pressure and temperature profile, and the pressure transients downhole during a short production test performed at WW01 Watton Waven field in Dominica. But coupled reservoir flow is very useful if we need to simulate production forecast scenarios with a wellhead pressure control of well discharge. So instead of controlling the well production using a well deliverability model with fixed bottom of pressure, we use a fixed wellhead pressure to control the well discharge. And Flow Well is a wellbore simulator which has been integrated into ITOF2, and it provides such capability for vertical or directional wells producing from multiple feed zones with a limitation of pure water reservoir application. Similar capabilities have been also implemented in TAF2 US2 for H2O CO2 mixtures with wellhead pressure control, evaluation of steam rate at the separation station, and the activation of makeup wells. This has been done by Saipan and Marcolini and Battistelli in 2012. And also these capabilities are available in a TAF2 version in which the well flow wellbore simulator has been coupled by WestJet. Now, just to complete, something about geochemistry and geomechanics. Actually, there are geochemical capabilities, modeling capabilities developed in Afiat, a well-known code, and geomechanical capabilities in TAF FLAC. This is the old version, and the new version is TAF 3 FLAC 3D. And then there are also new codes in which both the geochemistry and geomechanics are can be solved together. Geochemistry is usually, geochemical capabilities is usually used for mineral alteration and silica scaling in a hydrothermal system under natural and production injection conditions, while geomechanics capability are almost used for fluid and heat flow and stress-induced phenomena, such as formation compaction and ground subsidence, stress-induced changes in the reservoir properties, and borehole failures. This probably will be application that will find quite a lot of interest in the upcoming times. So thank you a lot for your attention, and thanks to the International Geothermal Workshop Committee for its kind invitation. Bye.
Okay, thank you for your excellent presentation and eminent research, Mr. Alfredo Battistelli. We have one question for you today, and the question is from Marcel Christian Sufijo from University Manado. The question is, most of your publication are using Voronoi and as well as the grid block and EOS respectively. What is the major effect that influence the model if using those conditions? And what the advantage if compared with the simplified model using rectangular grid block and iOS1? For your information, Marcel Supijo currently working at PT Geothermal Energy as reservoir engineering and modeler. And I think he read all your report. Please answer the question.
Okay, thanks for the question. So as far as the Voronoi grids, I think the advantage of using Voronoi grids with respect to Cartesian grid is the flexibility in building the grids. I mean, the grids is more flexible in describing the geological features, and I would say also to build refinement around the production and reinjection wells. So this is, I think, is the main advantage of using Voronoi grids. As far as EOS1, which is for pure water, versus EOSG, which is for ternary mixtures, I think it depends on the fluids mixtures you are working with. Of course, there are situations in which the concentration of non-condensable gas and salts are so low that you can easily use EOS1 and you do not lose any accuracy in describing the thermodynamics of the system. In other cases, let's say the partial pressure of CO2 cannot be just neglected. So you need to include CO2 in the model. So it depends on the actual characteristics of your reservoir.
Okay, thank you, Alfredo. And since there are no questions, I would like to discuss something with you related to geothermal reservoir modeling. And as you talked about in the earlier of your presentation, you talked about the capability of the reservoir modeling. And how about the challenge in the reservoir modeling? Could you explain in detail about that? Because all the reservoir model has a risk and the uncertainty in the reservoir itself. For example, the resource assessment and the capability, how long for the sustainability. Could you explain more detail about the uncertainty and the challenge in the reservoir modeling?
Okay, of course, reservoir modeling is built on the knowledge we have about the reservoir. So actually depends heavily on geosciences and results and reservoir engineering studies, actually. So that is basically is the conceptual model that brings into the reservoir modeling all the uncertainties we have. So what we can do in reservoir modeling is try to handle these uncertainties. So let's say making more scenarios, and maybe more scenarios even for the when we build and calibrate the natural state model. I know that this is not, I mean, it's not easy because often we have tight time constraints when we work on modeling. So more often we go through the most probable conceptual model and then the reservoir model, and then we go building the natural state and calibrate the natural state on this basis. But we know that depending on the stage of numerical modeling, if you are working with a greenfield, for instance, so there are big issues when we work with a greenfield. I mean, we usually have a few number of wells. We do not know exactly the boundaries of the system and how those boundaries will behave during reservoir exploitation. So I think that most of the uncertainties comes from the knowledge and then from all the studies we have coming from geosciences and reservoir engineering.
Okay, thank you. Mr. Alfredo, we have a question from Mr. Ali Asad. I think he's one of your friends. Okay, the question is, do you face the same problem that modeling tracer in TAF2 is very difficult to match the tracer concentration? What is the rationale behind this? Matching the arrival time is still achievable, but difficult in terms of concentration.
Yeah, one of the problem with modeling tracers and reservoir modeling is the quite huge dispersion, numerical dispersion we have. Unfortunately, when we build numerical models, we cannot use very fine grids for obvious reasons. I mean, because we would achieve reasonable computing times and so on. And usually using blocks of, let's say, tens of meters or hundreds of meters, more than enough. But when you go to tracer modeling, then we would like to model the transport of a tracer and the effects of numerical dispersion of our grid often make this exercise very, very difficult. So what would be needed is, a coupled solution of numerical flow within the reservoir, and a solution of tracer transport which is not based on numerical. I mean, and there are already some approaches that can do that.
Okay, there is a following question from Mr. Ali Asad too. It seems you are not using the dual porosity. Is there any basic reason that you avoid?
Okay, let's say that most of the models I built in the last time were related to greenfields. So often we had only a limited number of wells and a limited knowledge actually of the reservoir. So at this preliminary stage, we prefer to use, let's say, a simpler approach. We're using just a porosity model instead of adding a double porosity. I know that double porosity in fracture systems should be the choice. You then add additional unknowns to all the unknowns that we already had. So this was the main reason for the choice.
Okay, thank you, Mr. Alfredo. I think that's enough because we have a limited time. Thank you so much for sharing your time and experience with us. Hopefully the presentation from the invited speaker will be beneficial for everybody who has interest in geothermal numerical modeling. It's been a pleasure with you, Mr. Alfredo. Thank you.
Thank you.
Please give us an applause.
Thank you, Tavo. Thank you, Pa.
Thank you so much. Hello, ladies and gentlemen. We will proceed to the technical speaker. Let us welcome Afiat. As our first speaker, he is a student from Geothermal Master Program. As a part of student, he also has internship experience as a seismic engineer in Lemigas and also as a research assistant in Universitas Pajajaran. At this moment, he will deliver a presentation about reservoir modeling. Mr. Afiat, the Zoom is yours.
Hello everyone, my name is Afiat. I'm a student from Geothermal Engineering Master Program, Institut Teknologi Bandung, Indonesia. On this occasion, I will present our research on reservoir simulation with the title Danarano Geothermal Field Conceptual Model based on natural state modeling. This research was conducted by researchers from Institut Teknologi Bandung and the PLN or National Electricity Company in Indonesia. Broadly speaking, this research was conducted with a study related to the background of geothermal exploitation in this region. Geoscience studies are carried out to determine the features and characteristics of the geothermal field. As an initial exploration step, geoscience studies produce temporary conceptual models that will be updated in this study. Adjustments are made to form an appropriate simulation model in order to obtain results that are close to the actual natural state. Updated conceptual models are generated from natural state modeling results. The Danau-Ronald geothermal working area was established through a decree of the Minister of Energy and Mineral Resources in 2011. The geothermal field is located in the Lampung and South Sumatra province with an area of around 127 square kilometers. Danau-Ronald geothermal field is a virgin geothermal field assigned to Indonesian National Electricity Company to be developed. Until now, the exploration stage that has been carried out by the National Geological Agency only has limited data, which depends only on geoscience studies like geology, geochemistry, and geophysics. The result of the integrated geoscience studies are used to estimate the conceptual model of the Danau-Ronald geothermal field. At this field, there are no exploration wells or gradient temperature wells that have been drilled in this area. However, we assume that the results from geoscience are enough to support the physical parameters needed by the numerical model to be developed, including reservoir geometry, reservoir temperature based on geothermometers, and estimation of subsurface physics. Numerical model simulation is expected to be able to overcome the shortcomings of geological conceptual models and provide more precise and accurate estimation of subsurface features. The Ronald geothermal field is a Pleistocene caldera from Mount Ronald formed on the Sumatra fault system, which formed a basin due to the formation of a polypart fault system. The southeastern part of the Ronald formed Mount Seminung, which is a stratovolcanoes type post-caldera mountain. The products of Mount Seminung are lava and pyroclastic that show explosive eruption with high energy. According to the experience position of the manifestation, it is estimated that the remaining magma erupts as a heat source of the emerging manifestation that originate from Mount Seminung. Permeable zones in the Danau-Ronald geothermal field are controlled by Sumatran fault system, which is a strike-slip fault with a dextral moving direction that is relatively directed to the northwest-southeast. The separation of the fault section by step-over with an echelon pattern results in the formation of extension movement that forms volcanic tectonic depression at Danau-Ronald. And then Danau-Ronald geothermal field is indicated by the presence of surface manifestations in the form of hot springs and warm springs without any streams of gas manifestation indication in the surface. A detailed study of this report was carried out through 10 data of surface manifestation of thermal spring consisting of 4 hot springs about 55 to 63 degrees Celsius and 6 warm springs less than 50 degrees Celsius that spread on the slopes of Mount Seminung following northwest-southeast fault direction, which is Kota Batu Fault, and northeast-southwest fault, which is Lombok Fault. The geothermal hot springs and warm spring distribution is limited to only those 2 areas, whereas in the southeast section there are traces of the hydrothermal process in the form of argillic alteration on the surface, which is also associated with the northwest-southeast faults. Travertine deposits are also found to be associated with the presence of several thermal springs, followed by high bicarbonate value. The quality of manifestation data based on the ion balance analysis is excellent, with an ion balance value of less than 5%, based on Nicholson geochemistry standard published at 1993. Talang Biak and Kota Batu Fault act as a permeability structure based from gravity and magnetic method, and the low resistivity value found at depth of 200 to 500 meters below, with thickness about 500 to 1,000 meters. Based on the geoscience study, the conceptual model of geoscience that can be produced is what is seen on this slide. This geothermal field is high-terrain geothermal system that created by post-caldera eruption. The reservoir temperature is between 200 to 210 degrees Celsius, which Mount Seminung act as geothermal heat source. The outflow are located at northeast region, It is Cukuh, Wayuwangi, Kota Batu, and fringing manifestations, which the richest area spread over area of 54.25 square kilometers, mainly in steppe hills around Mount Sumimu. This research methodology is in developing the natural state reservoir model consists of several steps. It starts with collecting geoscience data and conceptual models from the latest study. The computer numerical model based on the conceptual model is made using a TAF2 simulator to simulate fluid and heat flow process of the geothermal system. This numerical model consists of grid blocks in which each block is assigned with the material properties. Top, bottom, and boundary condition of the model are set based on the conceptual model. The model is run to get the result of the model. The material properties, top, bottom, and boundary condition are calibrated iteratively to obtain the best match between the model and the conceptual model, which indicates that the model successfully represents the natural state condition of the reservoir. This model uses EOS-1 for water non-isothermal because of the data limitation and to simplify the modeling process. The grid of the model is rotated at 30 degrees to the north to accommodate the material assignment to be necessary in arrangement with the alignment of the conceptual model. Simulation model covered based from surface manifestation and permeable force distributions in these geothermal fields. The adjustment of grid size depends on the reservoir and permeable structure predicted position from geoscience maps. It covers a total area of 10 kilometers times 4.6 kilometers, or equal to 46 square kilometers, and a total thickness of 2.50 to 3.37 kilometers. The horizontal dimension of grid blocks varies from the smallest 200 meters times 200 meters to the biggest 474 meters times 474 meters. The smallest grid size is set to accommodate more detailed calculation on the reservoir part. The model is divided into 8 layers and 11 sub-layers, with some of the top layers following the real topographical condition. The total number of grid blocks is about 11.5 thousand pieces by using rectangular grid type. Some physics parameters are determined to form a model that approach the real situation in this geothermal system, which is hydrostatic pressure and normal temperature gradient were used at initial condition. The top boundary was set to be in atmospheric condition. Material in line with fault defined to be more permeable. The side boundary was assumed to be no flow boundary and treated to be impermeable materials. Bottom boundaries are heat source and impermeable rock or bedrock. The model consists of 8 layers that define based from general, medium enthalpy, high terrain geothermal system. Rock density, porosity, permeability, thermal conductivity, and specific heat capacity was defined. The initial condition is needed to input the initial temperature and pressure for each grid block on the model to fasten the process in running the model. At the initial condition, the normal gradient is used for both temperature and pressure. Atmosphere is applied to the top boundary condition by assigning pressure and temperature in the atmosphere or surface are homogeneously at 1 bar and 25 degrees Celsius respectively. Lake water in the Navarino area is modeled as a material composed of water, so it is defined as a separate material layer. It is done to accommodate the calculation of the existence of lake water intrusion in the geothermal system. Inside the boundary, it is assumed that there is no flows of fluids. All the side boundaries are in impermeable conditions, which is there are no flows of both heat and mass coming into or going out the system during natural state condition. To get optimal unreliable results, some adjustments are made to get results that are in accordance with their natural state. Some of them are by adjusting the temperature and pressure of the heat source, adjusting location of heat source in bottom boundary, adjusting permeability structure in X, Y, and Z directions, adjusting material properties such as porosity, rock density, thermal conductivity, and specific heat, adjusting the size grid blocks of capital, reservoir, and heat source, Based on the simultaneous process, the distribution of permeability gives impact to ability of rock to flow, the fluid and flow distribution of temperature, conductive and convective heat transfer. Convective heat transfer may occur in permeable zone or reservoir, and conductive heat transfer may occur both in the permeable and impermeable, like reservoir and cap rock or the boundary. So based on the result of numerical modeling of natural state, the model could determine reservoir characterization. 2 dummy wells were made to represent the hot spring manifestation at the Andrian geothermal field. Dummy wells are estimated by setting the well deliverability value at atmospheric pressure and certain productivity index to fit mass flow based on the field condition. In the process of eliminating the model, subsurface temperature valuation was carried out based on the 3D isothermal estimation method based on the idea of calculating subsurface temperature gradients. The calculation is done by determining the reservoir temperature based on the geothermal and reservoir and temperature of the surface manifestation. Then the subsurface temperature for its depth can be obtained. Boiling point versus depth, or BPD curve, are plotted to determine the characteristic of the reservoir. Based on the BPD curve, the interpretation shows that the reservoir is in compressed liquid state. This can also be confirmed from the SG or synthetic gas value in the modeling results. This figure shows the temperature of and pressure profile of dummy well 1, dummy well number 2, and dummy well number 3. They are located in the outflow zone, and then on the dummy well 3 that is located at the upflow zone, or that we create for this model. So we get the updated conceptual model shown in the figure. Was designed based on a preliminary geoscience study without any well data and submitted to create a numerical model approach. It appears that hot geothermal fluid flows upwelling from the deep part of non-seminal magma intrusions to the surface by rock permeability and porosity. The deep leakage of fracture permeability from Talang Biak Fault and Kota Batu Fault control the flows of hot fluid that ascend through the vertical permeability, with some fluids flow in the lateral direction. In contrast to the initial model, there is a change in determining the depth of the top reservoir, as the updated model has followed the interpretation of magnetology. It is stated that the top reservoir of Lombok geothermal area is situated around the depth of -500 mean above sea level. The only exception applied for the Kota Batu area, in which the reservoir reached the depth of -700. The geothermal line is determined based on the contours of subsurface temperature variation resulting from natural state modeling. The shape of the contour and the distribution of temperature factors are then adjusted to the available geoscience information. Contours and mass flow pressure factors show undulation patterns according to the geothermal field condition of the high-terrain volcanic system. To summarize, reservoir numerical modeling can be done by preliminary study data. The first natural state modeling of the Andrian geothermal field has established successfully by only the geoscience and Indonesian volcanic hydrothermal system approach. The mass and heat flow profiles predicted for new conceptual model. Range of productive zone or reservoir are between 13.65 square kilometers and 16.58 square kilometers, which reservoir shape is like a dome. Maximum reservoir temperature is 269 degrees Celsius, and geothermal system is liquid dominated. This natural state model can be used to predict the condition at the unexplored part of the reservoir. The conceptual model will continue to update it based on the additional exploration information to be carried out. Natural state modeling can be improved by adding subsurface information with exploration well, but both thermal gradient wells and slim hole wells. As an initial step of feasibility study, this model can be used to determine resource assessment using the Monte Carlo simulation method. This is the end of my presentation. Thank you for your attention.
Okay, thank you, Mr. Afiat. How are you today? Mr. Afiat?
Fine.
Okay, there is fluent presentation and we have several questions for you. Are you ready to answer?
Yeah.
Okay, the first question is from Arifin Ilham ITB. And I think the question is, I think that is a greenfield geothermal model since this field hasn't any well drilled. How can you ensure that the model achieve the natural state and please describe the actual condition? Is there any matching process with the manifestation? Thank you.
Okay. So basically, we doing some modeling is from the natural state that we create the dummy wells that spread over in the surface manifestation, the outflow, and then there's two manifestations that we use to create the dummy wells, and there's one dummy well that we create in the predicted upflow zone. So there's one artificial dummy well. So there's we create that, become the condition of the reservoir based on the 3D isothermal estimations, and then we check cross-check the geothermometers that have been studied from the geochemical research and the geological, and then we plot the BPD or the boiling point depth, and then based from the BPD curve, it's shown that there is no saturated gas, so we can confident with the water dominated reservoir in the Ranau geothermal field.
Okay, thank you, Afiat. And the next question is from Supijo, ITB. Since you have limited data to build the numerical model, how confident you determine the lateral boundary of the reservoir? What consideration did you use? Please answer the question.
We do some consideration based from the geological studies. There's a several condition that there's a ceiling, probably ceiling structure or ceiling fault structure. There's in the Talang Biak fault and the Kota Batu fault. There is no permeability over there, so we assume that there is a non-permeable zones. So we assume that that location to be the boundary condition for the models, and then the models for the vertical model is based from the water in the Danau or in the lake of Lake Ranau, and then the bottom of the vertical model is from the heat source or the magma of the heat source from this geothermal field.
Okay, thank you. And the next question is from Hasbi, ITB. I think this is the interesting question because I have several questions for you and he's the same like me. The question is there any significant influence from the presence of the nearest lake to the model of your geothermal system? Based on your experience, is there any influence? How did you overcome the impact?
Okay, that is that's one interesting question for us. That is the problem for these models. So we obtain some problem where we adjusting the models and the condition of the geological and geoscience studies. There's a spreading temperature gradient, and the pressure gradient is not normally in the stratovolcano forms, so it's not in the flat shape. So we made some condition like the temperature and the pressure or the heat flow and the mass flow from the models. We overcome that with the with creating the material that we assign it to be water in the Ranau.
Okay, thank you. And the next question is from Naldo Unima. Okay, the question is, how do you determine the outflow and the outflow based on the natural state condition?
Okay, so basically we assume that the outflow have the greatest temperature and the increasing the pressure. So we assume that the outflow is located nearby from the crater of the Mont Semino or in the center of the field. And then the outflow itself is located around in the spreading of the surface manifestation, like in Kota Batu manifestation, Lombok manifestation, and Talang Biak manifestation. It based from the temperature. We assume that the outflow located from the less than 50 degrees Celsius manifestation of 50 degrees Celsius temperature, and then the outflow is based from the more than 50 degrees Celsius from the BPD and then from the dummy well too.
Okay, one last question for you, Afiat.
Yeah.
Okay, it is from Lucas Doni, UGM. Okay, the conceptual model shows two symmetric reservoir on both sides, and it's very interesting, he said. How to prove this conceptual model is valid? Thank you.
Okay, so basically it's not two symmetrical reservoir. It's created, the reservoir itself is created like a dome, or you can say it like a upside down bowl itself. And then we do some cross sections in the moon, so it looks like two reservoirs, but it's not like two reservoirs. We do some cross sections that shown the reservoir itself is circulating around the Mount Seminung itself, and then the cap rock itself is covered the reservoir. So it is only contain one reservoir in the Mount Seminung. It's not two symmetrical reservoir.
Okay, many thanks, Mr. Afiat. It is very interesting presentation and good talk that you have fluent in the presentation. Thank you for your session. We would like to give you an applause. Okay, before we continue to the next presentation, there will be a video from our sponsor as commercial break.
Geothermal energy is a relatively environmentally friendly source of energy. It is derived from the heat of the earth. In recent years, the market for geothermal power has increased sharply, especially in emerging markets due to the economic growth due to the growing number of communities in low-income rural areas that have access to the power grid. Any governments are also increasing focus to reduce the dependency on expensive fossil fuels and not environmentally friendly. Systraco Group is a company engaged in the energy sector. Established in 1995, Systraco Group is currently very focused to be able to develop and serve you in various needs related to the geothermal sector, which among of them are hole cleaning services. Systraco Group provides comprehensive conventional fishing tools and systems include packer milling and retrieving, internal and external cutting, internal and external engagement, washover, basically every fishing application. Regardless of what's in your well, hence we've removed it successfully. We also provide a radial cutting torch that is safe and without any explosives or harmful chemical elements that can cut the tubular drilling equipment left in the well. As well, biochemical that can scale control, corrosion control, cooling water treatment and also as a rig washer. Downhole camera. Leveraging the advancement of technology today, Systraco Group also provides high-resolution downhole camera equipment and clear image quality and capable of operating up to a depth of 2,000 meters, adding to our line of services to focus on the development of the geothermal sector. Geothermal well testing. Energy Megaperseta as the sister company of Systraco Group also provides the services of geothermal well testing, real-time well monitoring, geoscience. Digital remote sensing used Sniffer 4D drone. Digital remote sensing system has an advanced capability to detect and map for the following energy sector applications: steam surface breakout monitoring, well reliability and integrity monitoring, air quality mapping, well surveillance and inactive well management, geothermal associated gases detector and mapping. All of which are focused to support activities in the geothermal sector. Please, do not hesitate to contact us when you need our support, because we are there for our common progress. Thank you very much.
Hello all participants. We have the second speaker today in this technical session. He is Mr. Jooned Hendrarsakti. Okay, he is a lecturer at Faculty of Mechanical and Aerospace Engineering and also a lecturer in Geothermal Master Program ITB. He has abundance of experience, as you can see in his CV now. In this session, he will deliver a talk about numerical study. Mr. Jooned Hendrarsakti, the screen is yours.
Okay, good morning. Selamat pagi. I am Jooned Hendrarsakti. I'm going to present my work with Maulida Rahma with the title Numerical Study of Temperature Profiles of Pression Flow in Geothermal Oil Field. The background of our works that first there are so many obsolete oil or gas wells that have potential moderate temperature of 50 about 100 degrees centigrade to be used for geothermal applications. So we want to know if these oil or gas wells is feasible for direct use geothermal utilization because it is not common yet in Indonesia right now. So we want to analyze using numerical methods since it is hard to measure or to calculate possible temperature as accurate as possible analytically. So the objectives of our study are, first, we want to generate the transient computational program of oil field geothermal gradient temperature using MATLAB. Second, we want then compare the result of our program. We want to compare the temperature profiles in the drill pipe and annulus as function of circulating time using current program compared to the literature simulator. We want to analyze then, after we compare, we analyze the feasibility of geothermal utilization in Arun field and BN field or in the decay area. In the building our program, we use double pipe heat exchanger, and this is coaxial double pipe heat exchanger. We divide it into 5 regions, and the first region is right here. This is the drill pipe region. The second region is drill pipe wall. This is between the region 1 and region 3, which the region 3 is the annulus region. And the fourth region is the interface between annulus and the outer pipe wall. And the fifth region is rock formations. The water is injected at the region wall, region 1, or at the drill pipe, and then until the bottom of the well, and goes up and extracted into annulus. And this is the numerical simulation scheme that we use. The first and the second, of course, is the continuity and the energy balance equations. These are that you can see here from the equation right here. This is only in the R and the Z direction. And also in the energy balance, also only in the R and Z direction. We didn't calculate for the theta directions. And also there are lowercase t here indicate this is the program for the transient flow. These two differential equations are then converted into arithmetic equation, the one right and the left. This is the simplification. And then after that, we can generate a big matrix to calculate the T1, T2, T4, and so on at a specific time. So if you can see this equation here, we have the subscribe, for example, M here indicate the location of the spatial, and then the superscribe indicate the time index. So the other parameters in our computational program are, for example, we need to know the water properties, rock formation properties, oil field data, fiber of design, and so on. We calculate the loss coefficient, and we have to know the boundary condition, for example, water injection temperature, water injection mass flow, and surface ground temperature. And we also need to know the initial condition, for example, water extraction temperature, surface temperature for region 2 and 4, and bottom hole temperature for region 1, 2, 3, and 4. The program that we build, they has the main program and 18 subroutines. The 18 subroutines, for example, there are initial gradient subroutine, velocity calculations, and so on, including at the end, for example, here is saturated water enthalpy or the properties of the water. So the validation of the current program, we compared with the well-bored model from Santoyo, Gutierrez, 1997 as reference. In comparison, the pipe diameter is about 0.2191 meter, the depth is 6100 meter, with the drill pipe diameter of 0.1143 meter. With operating condition are fluid flow rate of 15.14 kilogram per second, geothermal gradient temperature of 0.0292 centigrade per meter, and inlet fluid temperature of 57.2 degrees centigrade. And the result here that we can see here on the left for the drill pipe fluid temperature. On the right is for the annulus fluid temperature. So this is on the coordinate is the depth. We have until about 6,000 meters, 6,100 meters. So the result on the drill pipe here, first we can see our results indicate with the straight line here, the red and the green color, while the Santoyo and Gutierrez results are indicated with the line right here. Little bit has an arc line here. So, and then the other straight line here, you can see this is the formation gradient temperature. So you can see here the result little bit different. Our program with the Santoyo Gutierrez program are different. Not exactly the same, but the temperature result is about the same. Yeah. So the difference itself is due to the lack of informations, such as like start in time, temperature, and so on, that we cannot find in the original work of Santoyo and Gutierrez. And although the result will be different, the temperature range remain about similar. So we are confident that we can use our program to do some feasible study. And almost forget here, this is the one on the right. This is the picture of the well-bored depth with the annulus fluid temperature. Similar to the drill pipe fluid temperature, we have the straight line results. Yeah, with almost about the same. So you can see here this the time, circulating time, about 2, 5, 10 until 24 hours. Again, the temperature, although is not exactly the same, but the range is about similar. So we are very confident we can use the program to apply to other locations. So these are the data we apply to other locations. The location that we use is the Arun field and then BK area or BN in the BN field. The depth is about 3,000 meter and about 700 meter, with the temperature of the bottom is 178 for the Arun field, and the BK area is about 99.17. Yeah. So with the diameter of inner pipe is given here. This is the first column here for the Arun, the second for the BK area. Also the water injection temperature, water mass flow rate also are obtained here. And then the BK fields here, we have the other information like the temperature at the deepest point at region 1, 2, 3, and 4. Yeah. So these are the results when we apply our program into each field. On the left is the Arun, this is the depth. So and then we have the temperature. So the depth is about 3,000. Yeah, the result also indicate that it has about 130, 140 degrees centigrade after 24 hours when we circulating the water. On the BN field, when we circulating until 24 hours, the temperature remain lower than 70 degrees centigrade. So we can conclude that in the Arun field, it has about the maximum 130 degree. We classify it as geothermal source as moderate temperature source. For the BK field, this temperature about 80 degree. We don't think that's going to be higher than that. We classify into low temperature source. So in conclusion, that we have developed the transient computational program of oil field geothermal gradient temperature using MATLAB. And the results is, although it's little bit different from the result by Santoyo and Gutierrez, the results are similar. So we are very confident. So when we apply into the oil field, the obsolete oil field, for example, Arun is feasible as the moderate temperature, while the BN field is feasible to be converted into the low temperature geothermal source. Thank you very much, and I hope you enjoy our presentation. Thank you.
Hello, Mr. Jooned Hendrarsakti. Could you hear my voice?
Okay, sir.
Okay, how are you today, Mr. Jooned?
Very good, very good.
Okay, I'm truly appreciate and impressed with your research, Mr. Jooned Hendrarsakti. It is exciting and informative presentation. We have several questions for you today, and I would like you to present the presentation from the Algae ITB. The question is, did you consider the property of each rock formation layer in the calculation? Please answer the question, Mr. Jooned.
Well, we considered only the temperature near the wall. Yeah, we didn't like because the information is not complete, so we cannot. The only that we can use is just like assumption of the temperature of the rock formation. But for the layer of the characteristic of the rock, we didn't have the information. So I guess the answer is we didn't.
Okay. Okay, for the next question is from Dimas Taha Maulana from ITB, and the question from Dimas is, in the slide of the validation, in the temperature profile comparison in the drill pipe and the annulus for validation case with changing fluid property based on the simulation, why below minus 5,000 meter depth all the temperature have a reversal? It is the effect of cold water influx. Please explain this clearly.
The reason first is because the boundary condition. The boundary condition that what's at the bottom must be the same as whatever the initial conditions. So that's the main reason. So that sometimes in the computational simulation, the temperature must must be get adjusted due to the temperature at the bottom. Yeah, that's the main reason.
Okay, thank you. And the next question from Ade from ITB. His question is, could you explain the main reason why the temperature in BN field on the BK area in the simulation of circulation time about 5 hours have an identical value with the formation temperature, while the others don't have the same trend?
Okay, can you repeat again? Sorry.
Okay, in the slide of application of oil field data, could you explain the main reason why the temperature in BN field on the BK area in the simulation of circulation time about 5 hours has an identical value with the formation temperature, while the others don't have the same trend?
Okay, because this is a transient. Sometimes in the numerical simulation, it's not steady yet, the temperature. So it's simply due to the numerical simulation itself, not the. So it might be something that we have to go investigate it more, but I think it's more like the numerical scheme that we use.
Okay, one more question.
Like yes.
Okay, this is the last question, Mr. Jooned. It is from Andrian, ITB. Could you explain the benefit of your research using this method, and what is there any research development that there will be carried out in the future?
The main, at the beginning, it says that we want to investigate the oil and the gas field that already abandoned by the because we believe there are still some potential energy there that we can generate some heat for, especially for the direct use utilizations. Yeah, that's the main motivation too for the study. Does it answer the questions?
Okay, and I think we still have 1 minute left. And one more question and quick answer, please, Mr. Jooned. It is from Hendrarsakti. From your model, what is the water injection flow rate? How about the influx of the reservoir? Is there any preparation info? It is full reservoir preparation or certain part only? Thank you.
The water injection flow rate, I think, is somewhere. I think I put somewhere in the slide. It's about the flow rate is about 15 kilogram per second, and let me see. So what's the question again? I mean, what the other question I missed?
You mentioned there is an from your model, what is the water injection flow rate?
Yeah, okay, that's about 15 kilogram per second. And then the only water that comes is from the one that injected. Okay. There is no other source of water especially from the wall of the well. So I think that's one of assumption that we use in our study.
Okay, is there any information about the perforation info?
There is no. There is no such information. Yeah, because we didn't have enough information about like the well information, the well temperature, the well additional water source from the at least from the source that we get. Yeah.
Okay, thank you, Mr. Jooned Hendrarsakti, for your excellent presentation. I would like to give you an applause as our appreciation.
Thank you.
Okay, before we turn to the third speaker, there will be a commercial break from our sponsor.
Indonesia merupakan salah satu negara yang memiliki potensi energi panas bumi terbesar di dunia. Saat ini, Indonesia menduduki peringkat 2 dunia sebagai negara penghasil listrik dari energi panas bumi. Selain sebagai energi yang bersih dan berkelanjutan, peran energi panas bumi sebagai baseload penyediaan listrik menjadi pertimbangan utama agar pengembangannya diprioritaskan. Oleh karena itu, dalam menjaga ketahanan energi suatu negara, energi panas bumi dapat menjadi andalan untuk memasok listrik guna memenuhi target bauran energi 23% EBT di tahun 2025, sesuai dengan amanat dari Kebijakan Energi Nasional. Untuk memenuhi pencapaian target EBT, dalam bauran energi tersebut, Indonesia layak melakukan percepatan pembangunan proyek PLTP di Indonesia. PT Geodipa Energi Persero adalah perusahaan yang bergerak di bidang energi panas bumi mulai dari eksplorasi hingga eksploitasi. Perusahaan didirikan pada tanggal 5 Juli tahun 2002. Kemudian pada tahun 2011, melalui Peraturan Pemerintah Nomor 62 Tahun 2011, Geodipa ditetapkan sebagai Persero yang pengawasan dan pembinaannya berada di bawah Kementerian Keuangan dan PT PLN Persero yang juga merupakan salah satu Special Mission Vehicle atau SMV di bawah Kementerian Keuangan dengan misi mendukung program pemerintah dalam penyediaan listrik tenaga panas bumi yang aman dan ramah lingkungan, serta memberikan manfaat besar kepada Indonesia. Geodipa siap untuk melanjutkan pengembangan proyek PLTP di Patuha yang masuk dalam Fast Track Program atau FTP, tahap 2, 10.000 MW. Bagian dari program 35.000 MW yang merupakan program pemerintah di bidang pembangunan infrastruktur ketenaga listrikan.
Hello, ladies and gentlemen. We have the third speaker in this session. He is Mr. Zagy Yakana Berian. He is a fresh graduate of Mechanical Engineering Bachelor Program ITB, and he has plentiful experiences in a young age. For your information, his experience are an assistant lecturer at the Faculty of Mechanical and Aerospace Engineering ITB, and internship program at PT Pertamina Drilling Services Indonesia. Business consultant at Koperasi Astra International, and he is a chairman at Society of Renewable Energy ITB. In this session, he will deliver his research about hybrid geothermal power plant. Mr. Zagy Berian, the Zoom is yours.
Hello, everyone. First of all, let me introduce myself. My name is Zagy Yakana Berian as the first author and Mr. Hendrarsakti as the co-author. Today, I would like to present a system design of a solar and geothermal hybrid power plant for the Flores Island. This is the outline. Introduction, literature review, methodology, result and discussion, and conclusion and recommendation. Introduction. Indonesia has abundance of solar and geothermal energy potential, and Indonesia has the lowest electrification ratio with a number of 84% in 2019 and located in East Nusa Tenggara. Flores Island, one of the islands in East Nusa Tenggara, has abundance of geothermal and solar energy potential. This work will utilize geothermal and solar energy potential because it's very promising in the future. And there will be project development in Ulumbu 3 and 4. And the last is high generation cost or BPP with a price of 0.175 USD per kilowatt hour. In this figure, we can see the lowest load is in a range 0 until 6, and the highest load is in a range 20 to 24. And then the probabilistic duration of sunshine, or the LPM, in the Ulumbu is in a range 4 until 8 hours. And then this is the hybrid system literature review. There are 4 types of solar collector, but the most mature technology is parabolic through concertator. And then this is the north-south alignment and east-west alignment. For example, north-south alignment. It means the solar collector track the sun from the east to the west and vice versa. And this is the type of thermal energy storage, sensible, latent, and the chemical. And this is the alternative configuration of hybrid system. The solar collector can be placed in A1, A2, or A3. And this is the formula that used in this work. Beam irradiance based on the specific location, to obtain the beam irradiance and diffuse irradiance. And this is the solar radiation, the area under the curve. And this is the heat exchangers formula, solar collector formula, geothermal formula, thermal energy storage formula, and carbon dioxide emission formula. This is the thinking framework. The idea is the system will operate in the two conditions. The first one is the geothermal standalone, and the second is the hybrid. The solar radiation will collect by parabolic through concentrator using the heat transfer fluid, and then it will be stored in thermal energy storage, and it will release to supply the heat exchangers, while the peak load, the production well, will go into the heat exchangers, and the steam quality will increase before entering the steam power plant. And then for the base load, the production well will going directly to the steam power plant. So this is the solar energy potential. This work will generate the irradiation data and irradiance data based on the empirical formula. These tables indicates the day selected, and this is the Olumbu coordinates. For the irradiance, first one, obtain the irradiance data. And second, find the average irradiance data in each month. And the third is select the lower quartile to represent in its time. And for the irradiation, first one, input the LPM as arranged to function that been generated using Excel regression. The second is find the average value between 2017 until 2019. And the third, delete the outlier data. And the last is find the average value from the existing data. This works using the Aspen HYSYS to simulate the mass and energy balance. The first one, choose equipment for the power plant, such as turbine, separator, valve, and condenser. And then build the single phase and hybrid model. The difference between the single phase and hybrid, there is a heat exchangers in hybrid system. And then run the system between quality of 0.56 until 0.71 and choose the suitable steam quality. And this is the thermal system. The output is the required energy for parabolic through concentrator, area of solar collector, and mass and volume of the thermal system. It will be evaluated in two alignment, north-south and east-west. And this is the carbon dioxide factor using the life cycle assessment. There are three types of the power plant: diesel power plant, geothermal, standalone, and the hybrid system. And this is the model of hybrid system in this works. When the sun is shining, the energy will be stored in thermal energy storage. And then in the evening, between 18 until the 24, the thermal energy storage will release energy to supply the heat exchangers. So, the geothermal working fluid will go into the heat exchangers, and then the steam quality will increase before entering the separator, and then the mass production will increase and lead the turbine produce more energy. This is the TS diagram. From the state 1, it will going to the state 2, and from state 1, it will going to the 2H, and the H is denote hybrid condition. And this is the solar thermal energy potential. In this figure, we can see that the north-south alignment will gain the higher energy than east-west. So, the system will choose the north-south alignment. And this is the local characteristic of solar energy between two alignment in 4 hours, 6 hours, and 8 hours. And this is the power plant specification. There are two conditions, normal condition and maximum condition. The capacity will be the 22 megawatt for the normal and 26 megawatt for the maximum. And then the turbine efficiency will be set 78% for the normal and 80% for the maximum. And the conversion efficiency 14% for the normal, and 15% for the maximum. The steam quality 0.65, 0.56 for the normal, and 0.66 for the maximum continuous rating. For the duration, 80 hours for the normal, and 6 hours for the maximum. And thermal energy from the test is 80 megawatt hour and 84 megawatt hour for the maximum continuous rating. And this is the thermal system. The system choose the north short and 6 hour probabilistic. It will require 3 hectares for the parabolic through concentrator. And for the mass and volume of thermal system, it will require around 5,000 ton for HTF in PTC and around 4,000 ton HCF in the test, and required 3,000 meter cubic for the volume of the test. And this is the carbon dioxide emission. For the geothermal standalone, it will reduce 86%, and for the hybrid system, it will reduce 93% of the carbon dioxide in amount of 5,000 megawatt hour per year. In this graphic, we can see that the solar geothermal will reduce significantly in terms of carbon dioxide. And this is the conclusion. The system will operate between 18 to 24 and select the north-south alignment, required power from the parabolic to concentrator in amount of 14 megawatt, and electricity increase is 4 megawatt electric, and collector area is 3 hectares. The volume of the test is 2 times 3,000 meter cubic. The annual carbon dioxide emission from the diesel, geothermal standalone, and the hybrid are 1,800 carbon dioxide equivalent per year, 260 carbon dioxide equivalent per year, and 125 carbon dioxide equivalent per year. So for the further recommendation, the more details in design of the test, solar data conducted by the experiments, and analyze the economical aspect. Thank you.
Hello, Zagy, Berian. How are you today?
Hello, I'm fine, thank you.
Okay, thank you very much for your presentation. It is very impressive research and fluent presentation, actually. We have several questions for you. Are you ready to answer the question?
Yeah.
Okay, the first question is from Ali Asaf from ITB. I think you know him very well, right? Okay, the question is, how many degrees Celsius the temperature in thermal storage, as it needs higher temperature than the geothermal temperature in order to make energy transfer happens? Please answer his question.
Thank you very much for the question, Mr. Ali Ashad. In this system, the thermal energy storage temperature, the highest is the 14 degrees and the lowest is 370. Is it answer the question? Probably. So the system, so the system use the synthetic oil and the nitrat salt, but the challenges to use the nitrat salt is the highest freezing temperature. So we have to maintain the cold storage higher than 250. And I said in the system, the temperature of the cold storage around 370 degrees Celsius.
Okay, thank you. And the second question is from Mr. Prihatmaka, ELC. Okay, the question is, thank you for your presentation. He said that. Did you already compare about the economics of developing of each solar and geothermal? Is it more cheaper in investigation by making it hybrid in terms of IPP if it sell to PLN?
Yeah, thank you for the question. Because the limitation of my skills and background, mechanical engineering, I don't calculate the economical aspect, but I do the estimation calculation. If we give the additional thermal system or solar thermal system, it required 50 million USD for the capex. But in terms of the LCOE, the hybrid system will makes the LCOE decrease from the solar geothermal standalone. So I think based on the laser, $10 per kilowatt hour.
Okay, thank you. And the third question we have Dinda from Universitas Negeri Manado. Her question is, in this heat exchanger system, what is the most influential for the heat transfer process?
Sorry?
In this heat exchanger system, what is the most influential for the heat transfer process?
So I don't know the most influential that you mean, but I think the very important in the heat exchangers is you have to set the enough energy to supply the heat exchangers. So we have to calculate the solar energy in the specific location due to the extreme condition. So if you have the extreme condition, the heat exchangers, you have to calculate and make it with the extreme condition. So I think it's very important to calculate the solar energy.
Okay, thank you. And the next question is from Aska, Supreme Energy. His question is, nice presentation, he said. By heating up to phase fluid, scaling deposition tendency would also increase. Yeah, we talked about the scaling. And did you also consider the scaling risk?
Yeah, thank you for the question. Yeah, I think the scaling deposition tendency would also increase, but in this work for the early stage, I don't calculate the scaling deposition. But if you want to do the further research in this solar thermal geothermal hybrid system, you have to know the data of the working fleet. But because the limitation of data, I don't calculate the scaling influence.
Okay, we have next question for you because we have several time left. It is from Andri Halim Trisakti. Yeah? He said, good study. The question is, how about the cost of electricity production? Which model is the lowest, geothermal or hybrid? The question number 2 from his is, how to arrange and how much energy come between the solar energy storage and the geothermal well? It is get into the heat exchanger.
Okay, for the question number 1, the cheaper is the hybrid. If you install the hybrid system in amount of a large capacity, you have you will gain the install the capacity in terms of 10 megawatt or 15 megawatt. The geothermal standalone will the cheaper model. And the second, how to arrange how much energy come between the solar energy. There is such valve to connect the energy, the heat transfer fluid to the heat exchanger. So we have to give the control to the valve, and we have to analyze how many solar energy that will supply the heat exchangers.
Okay, Zagy, Yakana, Berian, one last question for you. It is suitable for you for low enthalpy. The question from UD, Star Energy.
Yeah, I do some research for the low enthalpy. I think the highest challenge is to utilize solar energy to supply the low enthalpy. So we have to calculate the solar energy, and we have to store the energy to the thermal storage, and it will be needs the energy to supply 24 hours. Install capacity, it have to set the install capacity like 10 megawatt below.
Okay, Zagy, Yakana, Berian, thank you very much. It's a good talk and good presentation from you. Thank you too for your valuable time. please give us an applause. Okay, before we shift to the next presentation, there will be a video from our sponsor. Hello, ladies and gentlemen. We have fourth speaker in this presentation. He is Andrian Putra Wardana. Okay, Andrian Putra Wardana is a fresh graduate of Geothermal Master Program ITB. He has plentiful experience as a laboratory assistant, lecturer assistant, and he also internship practical training. In this session, he will deliver his presentation about heat loss in production well. Mr. Andrian, the Zoom is yours.
Good afternoon, ladies and gentlemen. Before I start this presentation, I want to give thanks to ITB International Geothermal Workshop 2020 Committee that have conducted this event. First, I want to introduce myself. My name is Andrian Putra Wardana. I'm from Geothermal Engineering Master Program, Bandung Institute of Technology, Indonesia. Today, I will present my research with my thesis supervisor with the title of Study of the Heat Loss Effect in Geothermal Steam Production Well. This is the outline of this presentation. First, we will start with introduction that consists of background and purposes of this research. Next is methodology that consists of flow process of this research. Next is case study that consists of well data that is used in this research. Next is result and discussion from this research. And the last one is conclusion and recommendation from this research. First, we will start with introduction. As we know, geothermal production well is a main component of the geothermal production facility and also a geothermal fluid flow media that connects the surface and the reservoir. A geothermal well is similar to oil and gas well that consists of casing and cement. During the geothermal production, it will be changed in the characteristic of geothermal well, such as casing and cement temperature will increase. That is due to heat loss of the geothermal fluid. During the geothermal production, the heat transfer will occur in the well by conduction and convection heat transfer. The convection heat transfer is the heat transfer that occurs between the geothermal fluid and the inside of production casing, and the conduction heat transfer is the heat transfer that occurs between the casing and formation. There are several factors that influence the heat transfer in the well, such as well, cement, and formation specification. The fluid characteristic is also influence the heat transfer in the geothermal well. The heat transfer will cause the temperature change in fluid, casing, and cement. This is several purposes from this research. First, this research is development of heat transfer model in the steam production well. Second, this research is to predict the steam heat loss and its effect on every 100 meter well increment when the steam is produced, and to predict the temperature distribution of casing and cement and their effect on every well segment. Next is methodology. This is the flow diagram of this research. This research is start with literature study that supports this research. From the literature study, we will get the well data that we need for this research. Next is well data interpretation of one geothermal well. Next is development of heat transfer model and calculation using well sim. For heat transfer model development, first we input the parameters of casing configuration, well geometry, and formation temperature. Next is pressure drop calculation using homogeneous flow model. Next is heat transfer model development by input the heat transfer equation. Next is heat loss calculation, and we will get the fluid pressure and temperature from heat transfer model calculation. And then for well sim calculation, we start with input parameters. That parameter is similar to the parameters that we use for heat transfer model calculation. Next is calculation with well sim simulation with bottom-up calculation, and we will get the fluid pressure and temperature from well sim simulation. Next is comparison of model result and well sim result. If the model is not matched with well sim result, we must check the heat transfer model development, such as we must check the equation of heat transfer or the input parameter to heat transfer model. And if the model is matched with well sim, we can continue the next calculation, such as heat loss calculation every 100 meter of well increment, and casing and cement temperature calculation and distribution. There are several limitations from this research. This model is using the Fourier's law and Newton's cooling law. That the Fourier's law is used to conduction heat transfer calculation, and Newton's cooling law is used to convection heat transfer calculation in cylindrical media, and is also using the Remy heat transfer that was developed by Horner and Shinohara to calculate the steam heat loss. And then this research is also the pressure is calculated using the homogeneous flow model in this research. And this model is developed in the steam production well during the production activity. And then there are several assumptions that is used in this research. First, the well static temperature is assumed as the initial temperature of casing, cement, and formation. Second, the formation temperature is assumed to be unchanged because the condition of heat transfer is there are a different temperature in this research. The different temperature is between the geothermal fluid and formation. And the last one is the heat transfer that is occurred in liner is neglected because in the liner there are several production zone, and we need the reservoir simulation to calculate the heat transfer in the liner. Next is case study that consists of well data that is used in this research, and well A01 is used in this research. We have composite log of well A01. From the composite log, the continuous epidote is at depth of 707 meter and is assumed as top of reservoir. And from formation lithology, there are two indications of formation lithology. First is andesite is at depth of 0 until 300 meter and 459 until 1,600 meter, 608 meter. And the second one is breccia-tuff from depth of 300 until 459 meter. And we have the pressure and temperature static of well A01, and this is the graphic of PT static of well A01. From the graph of PT static, the temperature static is higher than the boiling point per depth or BPD, and is assumed that the reservoir fluid of well A01 is superheated steam with the reservoir temperature of 224 degrees Celsius. Next is result and discussion of this research. This is the result of model and well sim comparison. The comparison is conducted to validate the model result with the well sim result before being used for next calculation. And from the graph of pressure and temperature of model and well sim, the steam pressure and temperature of model is matched with the steam pressure and temperature of sim. It is shown that the trend of pressure and temperature of model is the same trend of the pressure and temperature of the sim. And from this result, we can conclude that, that this model can be used for next calculation. And then this is the result of steam heat loss calculation. From the graph of heat loss of at every increment, the steam heat loss is less than 2 watt per meter at every increment. And the steam heat loss is increased along with the increase of well increment. And then the formation temperature drop is also calculated in this research. The formation temperature is increased along with the increase of well increment. And then from the graph, the steam heat loss and the formation temperature drop is increased along with the increase of well increment. And we can conclude that the formation temperature drop could affect the steam heat loss. And we can get the correlation that the heat loss of steam could be higher along with the increasing of formation temperature drop. And then this is the result of temperature distribution of casing and cement. And this is the result of final temperature of casing and cement at every well segment. With the segment 1 is at depth of 0 until 30.5 meter, and segment 2 is at depth of 30.5 until 459 meter, and segment 3 is at depth of 459 until 784 meter. And from this result, the casing and cement temperature is increased during the production operation, with the initial temperature is similar to the formation temperature, and there are different temperatures of every casing and cement. From the result, the heat of steam is estimated not completely transfer into the formation because the heat loss is very low, or less than 2 watt per meter, and the heat of steam is estimated only transfers to the surface casing. It is shown that the temperature difference of surface casing and surface cement is large, and the temperature of surface cement, conductor casing, and conductor cement are close to the formation temperature. And this is the visual of temperature distribution of casing and cement at every segment. And from the result, the material thermal conductivity and the thickness layer of well segment could affect the steam heat transfer. It is shown that the temperature increasing of casing is higher than the temperature increasing of cement. And because the thermal conductivity of casing is higher than the thermal conductivity of cement, and then cement can reduce the heat of steam. And the segment 1 layer is thicker than the segment 2 and segment 3 layers. It is shown that the segment 1 have 3 layers of casing and 3 layers of cement. And the heat of steam in segment 1 is estimated only transfer into the casing surface. It is shown that the cement, the surface cement, casing conductor, and cement conductor temperature are close to the formation temperature. And we can conclude that the casing and cement could have a lower increasing temperature along with the lower of material thermal conductivity and the thicker of the well segment layers. In this research, we use 75 watt per meter Kelvin for casing thermal conductivity and 0.5 watt per meter Kelvin for cement thermal conductivity. And next is conclusion and recommendation from this research. There are several conclusions from this research. It can be concluded that the heat transfer model result match with the well sim result. Then this model could be used to calculate the heat loss of steam and the temperature of steam, casing, and cement. The heat loss was very low during the steam production. Then the heat of steam won't completely transfer into the formation. The heat loss of steam could be higher along with the increasing of formation temperature drop. And the material thermal conductivity and the thickness layer of the well segment could affect the steam heat transfer in the production well. And then there are several recommendations from this research for further research and the usage of this model operation. This research needs to be validated with laboratory scale experiments or the field measurement. This heat transfer model can be developed with other pressure drop correlations such as Briggs and Brill correlation, Higginbotham correlation, or Krzyzewski correlation, and so on. And also can be developed for water-dominated production well and two-phase fluid production well. And for the usage of this model calculation is recommended to be conducted before the drilling activity in the casing and cement design to reduce the risk of drilling activity, such as the thermal shocking at shallow depth of geothermal well. And then there are several references that support this research. That is all. Thank you.
Okay. Okay, Andrian, thank you very much. How are you today?
Good, I'm fine.
Okay. Okay, can you hear me clearly?
Yes.
Okay. We would like to have several questions for you in the Q&A session. Are you ready?
Yes, I'm ready.
Okay, the first question from Albertus Ivan. He is from University Pertamina. The question is, why the result is validated with the well sim results, not with the field data such as PTS data? Okay, please answer this question.
Thank you for your question. Why the result is validated with the well sim result, not with the field data such as PTS data? Because we didn't have the PTS data of the field, so we only validated with well sim results. And then for the recommendation for the research is we need to validate with the field data such as PTS data or maybe from heating up data.
Okay, thank you. And the next question is from Hasbi. It's from ITB, and the question is, how do you consider different type of rock formation in your calculation?
Okay, thank you. For the formation temperature, we start from the composite log. We indicate the formation ecology, and we find the such as the thermal conductivity of formation, its specific formation, and we calculate it with the formula by Fourier's law, Newton's cooling law, Chemis, and Horne-Ensinara equation for the heat transfer.
Okay, thank you. And the third question we have today is from Andrian. It's the same from ITB. This question is still related to question number 1. In the segment 2, in your schematic wells, there are 2 types of rock formation. How do you calculate the heat loss in this area?
Okay, how to calculate for this area? We have the indication of 2 formation lithology at segment 2. We calculate with bottom-up calculation with the segment of 3 meter until the 0 meter, and we calculate it, and we calculate the result at the top of segment because it is more representative to determine the further research, such as to determine the casing and cement material that supports the well during the well heating up. So we calculate it too.
Okay, sounds good. And the third question we have from Taufik Rahman, ITB. Okay, this question is considering the fluid produced is the vapor phase in your in the well. In this calculation, could you predict the occurrence of the condensation in the wells?
Thank you for your question. We cannot calculate for the condensation in the well, and we assume that in the well that the condensation is not occur in the well during the production operation.
Okay. Okay, thank you very much. We have 4th question here. It is from Nur Hoiri Amin. The question is, could you please give us the benefits of your results to be implemented on the sites? And her second question is, what is your preliminary hypothesis and impact of heat loss due to scale formation?
Thank you for your question. Good. About the benefits of our research to be implementation on the site, it is the preliminary study, and we hope that this calculation is have a benefit for implementation in the site, such as for the determination of casing and cement material, and we can indicate the thermal shocking at the shallow depth of the well, and also we can determine the mud design, such as for the density of mud and the temperature of mud during the drilling operation. And the calculation is recommended to calculate before the drilling activity.
Okay, thank you, Andrian. And the last question in the session for you is from Dimas Taha Maulana. I think he's your supervisor, right?
Yes.
Okay, Dimas Taha Maulana asked a question for you. Have you done calculation with the different wellhead pressure to see the effect of the operational condition to the heat loss in the production wells? Please describe clearly because he is your supervisor.
Okay, thank you, Mr. Dimas Taha Maulana. About the calculation with another wellhead pressure, I calculated with one wellhead pressure, and maybe can calculate with another wellhead pressure. So I didn't calculate it with another wellhead pressure.
Okay, I think that's enough because our limitation time. Thank you so much, Mr. Andrian. There will be thank you, and please ask, give up an applause. Okay, Andrian. Okay, before we resume to the last speaker in the session, there will be a video for our sponsor. Hello, honored participant and audience. We hope you all in the high spirit in this afternoon. We have the last speaker, but not least, in the last day of technical session. He is Galih Kusumo Wardoyo. Galih Kusumo Wardoyo is a project engineer at PT PLN. His educational background is a master's degree in geothermal engineering. Before becoming a project engineer, he was a power plant engineer in the same company from 2008 to 2015. In the session, he will deliver his research, which is an application of artificial intelligence in geothermal production. Mr. Galih, the Zoom is yours.
Okay, thank you for this opportunity. Assalamualaikum warahmatullahi wabarakatuh. My name is Galih Kusumo from Geothermal Engineering, Bandung Institute of Technology. At this time, I would like to introduce the applications of artificial intelligence for prediction of geothermal reservoir productions. The outline of my presentations, the first is about the backgrounds, methodology, result and discussions, and the last is about conclusions. For the backgrounds, as we know that a reservoir is the main asset of geothermal exploitations, means that the problem in reservoir will affect to the continuity of the business of geothermal exploitations. And as we know that a reservoir has heterogeneous properties, it means that it consists of the uncertainty. And then currently, the reservoir production modeling use certain assumptions parameters. So it needs collaborations with geoscience study engineering to build the reservoir production modeling. And then we know the challenge that there is a lot of data recorded on geothermal operations that had not been properly utilized. And then the development of artificial intelligence offered the opportunity to be applied to the geothermal. And the last, about the development of computer technology. And then we have an idea that they use the artificial intelligence as the alternative method in the reservoir evaluations. Currently, the use of artificial intelligence is widely used in our lives. In the energy sectors, for example, for the oil and gas, as we know that now it has been commercialized. For example, the Baker Hughes that announcing the Baker Hughes C3.ai, and then Schlumberger collaboration with the Dataiku partnerships, and they will enable the enterprise scales of artificial intelligence in the exploration and productions. So the Halliburton. This idea and the methods we will implement into the Putra geothermal fields. That's the complex fields that consist of 10 geothermal wells and 1 injection wells. The total production is November in 2019. 2018 is about 360 tons per hour or 100 kilogram per second. This is a steam-dominated geothermal field. The brief methodology of the study is consists of, in general, consists of 3 parts. The first is about data preparations, that consists of data processing and determine input and output. Data processing consists of the data cleansing, data normalizations, correlation analysis, and the lag plot analysis to show the continuity of data. And then we build the artificial intelligence architecture by using the Python with the PyCharm as IDE, integrated development environment, and then supported by the project interpreters such as NumPy, Matplotlib, Neuralab, Pandas, Seaborn, Scikit-learn, and CP. And then after we build the architecture of artificial intelligence, we do the train and we validate the models. And then we validate the model by using the calculation of mean absolute percentage error. After that, we have the reservoir production model to prediction model. This is the architecture of artificial intelligence. We use the artificial neural network for this model that consists of input layer, hidden layer, and output layer. For each layer, it consists of the neuron that connected by the dendrite pathway, cause it called a weight factor. And based on the study of the data processing that we said before, that we set the input parameters as the wellhead pressures, wellhead temperature, trim valve open, megawatt, and reservoir pressures. And we have to predict the flow of geothermal wells. It's called free flow rates for the predictions. To know what is the best training algorithm that can implement to solve the problem that we have faced in the study, we have 2 alternative training algorithms. The first is about Newton conjugate gradient algorithm and the Broden-Fletcher's Goldfarb-Sano algorithm. And then to know what is the training method that the best solutions for the problem in our study, we use 3 kinds of method. The first, it's about the show in the figure A. It consists of only the percentage of use of data for training and the percentage data for the validations. We use the method 1 that's shown in figure A, and then method 2 shown in the figure B. And the last, the method 3 is we developed another method. It's called figure B with the random data. this is the illustration of simple implementation in a single well. We have production data, in this case mass flow, that we have to predict. In 700 days we have the actual data, and then we delete about 40% of the last 700 data, and then we use the remaining data to train the artificial intelligence. And then we simulate after we train, and then we simulate. So we have data predictions, and then the comparison between actual and predictions. We calculate the error. The error in this study, we use the mean percentage absolute error. So the two ways of this, what we do in this simple implementation. The first, the AI model that has been trained is used for prediction simulation, and the second, we calculate of the error of actual value and prediction value by using the mean absolute percentage error. And then, as we introduced previously, that we have two kind of algorithm, Newton conjugate and also Boulden-Fraser. We saw that the Boulden-Fraser's Curvasanos is the best algorithm that provides optimum in results. We saw in this graphic that this is better than the Newton conjugate. And then next, about the variations of training method. We have three kinds of training methods. The results show that the random training provides the minimum results, with the number of average error is about 1.6% in average. It's a mean absolute percentage error. And then the conclusions of our study. The first, the artificial intelligence model for precision geothermal reservoir production with the steam flow as input parameters has been successfully developed by looking the mean absolute percentage error that we said before. And then the second, the BFGS algorithm, Boulden-Fraser's Curvasanos, is an effective algorithm that in implementations of the prediction of model in the study. And then the third, the random methods of training and validation produce the minimum error with the minimum data usage. And then the fourth, the minimum average error values in the study is about 1.6 by using the BFGS algorithm and the random training methods. That's all. Thank you, and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Hello, Mr. Galih Kusumo Wardoyo.
Hello, Mr. Heru. How are you today?
You hear my sound crystal clear?
Yes, it's clear.
Okay, thank you very much. Mr. Galih, thank you again for your interesting and informative presentation about artificial intelligence. It's quite new in reservoir, especially in geothermal. We have several questions for you. Are you ready to answer that?
Yes, I'm ready. Thank you.
Okay, the first question is from Nindi. She is from Undit. The question is there any specific artificial intelligence configuration for the model used in your study to predict geothermal reservoir production?
Okay, thank you for the questions from Nindi. I think based on the literature, there is no specific configurations related to the architecture of artificial intelligence, but based on in our study, it's based on trial and error. And then the best configurations in this study is about 5 neuron in the input layer, and then 20 neuron in the hidden layer, and then 1 neuron for the output layers. I think it's enough.
Okay. The second question is from Fadil, I guess is from Universitas Trisakti. Okay, the question is, what is the best injection strategy based on your AI to earn the optimized production? If you could answer that, because it is not on your presentation, right?
Yes. Okay. Thank you. This is the further studies of the next study that I have published in the ITB International Geothermal Workshop. Based on our study, we can develop the optimizations methodology to optimize the geothermal field. Based on our study, I think the best is as conditions with the 30% of injections is about 30 kilogram per seconds. And then for the next, we predict it's about 20 years. We see that in the 10 years after that, we must shift the production strategy by the increasing the strategy of injections. The optimum injections that produce the maximum steam productions is about above 40% of injections is about 40 kilograms per second.
Okay, thank you.
Thank you.
The next question is, it is from Praja, PTPLN and ITB. I think it's your college.
Yes.
His question is, you are using Python script, and there are any certain consideration why you are using Python, and are there any challenge in implementation?
Okay, thank you. Why using Python? Because I think this is the easy to use for us for beginner programmers. And then the second is about it's free. And then related to the challenge is about the data. The data we only have about 3 years data, so it needs more data for the further analysis.
Okay, we have next question for you. It is from Prihatmaka, is from ELC, and he said that is very interesting topics. Okay, you mentioned about the input parameter is megawatt. Can you explain what is the correlation the megawatt with the other parameters from the wells parameters such as well temperature and pressure? Please answer that question.
Okay, thank you for the questions. The first is for this study, we have to predict the steam flow. So the inputs consist of megawatts, wellhead pressure, wellhead temperatures, and then as we know that the change in megawatt will change the productions of the steam flow. So it's been analyzed by the correlation analysis. Maybe I don't show in these presentations that honestly the megawatts, the correlation of megawatt with the steam is quite high for the steam that for the wells that have high steam productions.
Okay, thank you. You have many time for your question and answer session left. The next question is Gladys Rera. I think he is the same college as you from the PTPLN and ITB. Okay, the question is, do you apply some exception or constraint in this research? And how many minimum data wells to validate that your algorithm is correct?
Okay, thank you. These concepts, maybe it's called like data driven. So there is no exception. So, and then the best, I think, based on the result, the best percentage of data used is about 70%. And then I think because we only use about 3 years of production data, it's better to use this model for the short-term predictions, maybe 3 or 5 years.
Okay, sounds good answer for me. Okay, we have next question for you. It is from Andri, is from Trisakti, and he has several questions for you. The first is, why is BFGS method give better result than NCG method? Could you elaborate the key factor that affect this result? And the second question from his is, Why are you delete the 40% of the last data before you train the data? Is there any reason to use only 40%? Thank you.
Okay. The first question is about BFGS and Newton conjugate, yeah. Based on the literature,
okay.
As we know that the reservoir properties is consist of the unlinearity, not linear conditions. And then NCG and BFGS is the kind of the how to optimize the functions in mathematics based on the based on the literatures. BFGS use the second derivative to give the informations to how the directions of the optimizations. But anyway, it's only used to when we use the Python or for the project interpreter and the NeuroLab for project interpreter, we only type the train.bfgs, only train.ncg like this. So it's easy to use.
Okay, thank you. We have following question from Mr. Prihatmaka. I think he is not satisfied enough with your results. The question is, what do you want to try to predict or calculate about the flow, not the megawatt, because the production of the geothermal power plant is electricity.
Okay, thank you. These good questions. This is based on our aims. We can predict the pressure, we can predict the steam flow, we can predict the megawatts based on the data that we have, and then what we want to the next predictions like this. In this study, we use steam flow for predictions. Actually, we can use the pressure for the output of the models, and then megawatt for the output for the model. Is only the examples of use of this model for the predict the steam flow.
Okay, thank you. We have several questions for you, right? Because we have plenty of time. The second question from Mr. Bambang. He is from PTPLN and ITB too. I think it's his college. I think you're quite famous among your friends. Okay, his question is, what is the recommendation to improve your AI?
Okay, the first is about data. We need to update at the several times, and then as we know that we only use the 3 years data. So when we have new data, it can be input and then updated the model, and also the validations.
Okay. 1 minute left, and I have one question for you. I think I always ask about this question, and I will know from you. Yeah. Is this AI? I think it's interesting question for you and for all the reservoir engineer and modeler. Is this AI could replace geothermal reservoir numerical model in the future? Okay, please, I want to hear your perspective about this statement.
Okay, thank you. Based on my perspective, for example, for the first step of the building models, the data processing, it needs some kinds like expert judgment. So I think this is the reservoir engineer with including for the processing data of the first stage. Okay. And then for the further discussion, study, we need to validate maybe with the reservoir model, numerical model, for example, like this.
Okay, thank you very much, Mr. Galih. And I would like to personally thank you for your presentation. And I believe that our audience was intrigued by the new possibilities for AI application in geothermal energy. And I would like give an applause. And I'm sorry, I forget that Andrian. I would like to give an applause for both of you. Thank you very much. Give us applause.
Thank you.
Okay, that's it for the technical session. Before we jump to the next session, the last is the video from our sponsor.
PT Kogindo Daya Bersama adalah perusahaan ketenaga listrikan di Indonesia yang beroperasi di seluruh wilayah Indonesia dari Sabang sampai Merauke. Kogindo didirikan pada tahun 1998 sebagai anak perusahaan PT Indonesia Power dan bagian dari PT PLN Persero. Kogindo memiliki 4 bidang usaha, yaitu suplai energi, jasa operasi dan pemeliharaan pembangkit listrik, jasa gas dan diesel engine, dan jasa maintenance, repair, overhaul, MRO. Dalam kurun waktu lebih dari 2 dekade, kami telah mengembangkan bisnis kami secara signifikan dan membangun dasar yang kokoh bagi portofolio perusahaan di level nasional maupun internasional. Kogindo menawarkan satu solusi layanan terintegrasi di bidang ketenaga listrikan melalui Kogindo Integrated Solution. Dengan menggabungkan kompetensi, teknologi dan pengalaman, kami yakin dapat membantu para pelanggan mencapai efisiensi dan keandalan pengoperasian pembangkit listrik di Indonesia dan seluruh belahan dunia. Kogindo, trust.
Dear esteemed participant, finally we come to the end of the presentation. We would like to say thanks again for all the presenter of their informative and interesting talk, and to the audience for your active participation. And I would like to remind you all there will be a memento for you as a token of our appreciation for your valuable contribution, and then the committee will contact you regarding the shipping address. And that's the end of the day for the technical session. And hopefully the presentation will be beneficial for everybody. Thank you very much.
Thank you, Pak Heru Berian Pratama, for guiding us throughout the technical session. Thank you also for Mr. Alfredo Battistelli as invited speaker for interesting presentation, and congratulations for all the presenters for successful present their findings. Okay, ladies and gentlemen, special for our last day event, we will announce some exciting news as a token of gratitude and appreciation from the committee. Some presenter will be awarded with 2 categories. The first category will be best presenters, and the second category is the best topic presentation of each day event. So I will announce the best presenter of each day first. The best presenter for the first day is Bapak Muhammad Permadi Sugiharto from Pertamina Geothermal Energy. Please give applause. And for the second day, the best presenter is Ibu Betseba Sibarani from ITB. Please give applause. For the third day, the best presenter is for the third day, the best presenter is Ibu Rindu Intani from Star Energy. And the best presenter for the fourth day is Zagy Berian from ITB. So now I will announce the second category of best topic presentation of each day. So for the first day, the best topic presentation is from Ibu Mona Natalia from Sarula Operation Limited. And on the second day, the best topic presentation is from Bapak Mauliate Agustinus Sihotang from Supreme Energy. And for the third day, the best topic presentation is from Bapak De Santa Yuda from Sarula Operation Limited. And the best topic for the fourth day is from Galih Kusumo Wardoyo from PT PLN. Congratulations for all the best presenter and best topic presentation. The committee will contact you all regarding the certificate. Okay, without any further ado, we are cordially inviting Ibu Suryantini as the chairman of ITB International Geothermal Workshop Committee to symbolically end the series of our 9th ITB International Geothermal Workshop. Most welcome, Ibu Suryantini.
Good evening. Without realizing it, it turns out that we have spent 4 days together at ITB International Geothermal Workshop. Today, we come to the end of this annual event. It is time to say goodbye. But before I close this workshop, let me once again express my gratitude to all those who contribute and support this event. Thank you for the committee, and thank you for Geothermal Study Program, ITB. I know you have been quite a tough and exhausting, but at the same time, very inspiring and rewarding days and months. Well done. All of you have done a great job. I also thanks for the speaker and moderator that have shared their idea and knowledge to all of us. I firmly believe that we have learned a lot from them, and we hope to be able to implement every knowledge that we gain from you. I wish you all the best in your future career. Thank you for the endorsement from International Geothermal Association and also Indonesian Geothermal Association. We hope that we can strengthen and expand our collaboration, and I believe together we can develop geothermal energy for better world. Thank you for sponsor and support parties. We wish you success in every business program and activities at your companies and institutions. I congratulate to all of you, to every one of you, to each of you participant, and good luck for your future. I sincerely wish you find that one spark, that one brilliant idea that will change your lives and hopefully make the world a better place. I hope this 4-day workshop will benefit a lot for you. And I remind you to keep updated with new information from our website and other media channel. There is still one program left, and ITB International Geothermal Workshop Committee, together with Indonesian Association of Geology, will hold a webinar course. Please stay tuned for more detailed information. Geothermal Master Program, ITB, is committed to share knowledge and information to educate all the people around the world. We invite all of you to make a better world with green energy, clean energy, geothermal energy. And lastly, during this pandemic COVID-19, I know this time is not an easy time for all of us, but don't lose faith. Keep praying, because God is making a beautiful plan for the welfare of mankind. Stay healthy, keep working, keep praying, and God is with you and bless you all. And now it's time for me to close the 9th ITB International Geothermal Workshop 2020 and hope to see you again in the next ITB International Geothermal Workshop 2021. Thank you. I return to Angga as the host.
Okay, thank you, Ibu Suryantini, for the closing speech. Before we run off the last day, there will be a photo session for all panelists, including all invited speakers, presenters, moderator, lecturer, and the committees. For those who are mentioned, please activate your video. We are about to take photo. Okay, ready? The cue on me. 3, 2, 1, smile. Okay, thank you for all the panelists. Now, we are at the end of the 9th ITB International Geothermal Workshop. Due to the limitation of time, unfortunately, not all of the presentation can be brought to you during the event. But don't worry, other presentations are accessible for you to enjoy on our official website, www.workshop.geothermal.itb.ac.id /workshop 2020. For full recorded version of our event will be uploaded on Geothermal ITB YouTube channel. We would also like to remind you that ITB International Geothermal Workshop is an annual event, so stay tuned for more event coming to you. Eventually, this is the time for me to say goodbye. I'm Angga Bakti Pratama, your host for today, hoping to see you on the next ITB International Geothermal Workshop. Thank you and enjoy your evening. Bye.
I encourage you all to keep pushing geothermal forward. It's important for our world.
Welcome to the 9th ITB International Geothermal Workshop. First of all, I introduce Workshop Committee, as shown in this slide. They have worked very hard, great effort, and have done excellent work. Thank you, committee. Without your participation, this workshop will not be success.
Thank you for the invite as a speaker to deliver a speech on Indonesia geothermal development.
Great. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you very much.
Thank you very much.
Thank you. Thank you.
Thank you. Thank you.
Again, thank you.
Thank you very much.
Thank you.
Thank you very much. And see you again.
I look forward to seeing you in person somewhere sometime.